Hey guys, welcome to another video. So in this video, we are going to learn about low-level design patterns. So the reason why I'm making this is because I've often realized that people try to learn all 20 plus design patterns at once and then they forget that which design pattern we have to use in what scenario. So the way I'm going to approach this is that basically they are not treating them as some vocabulary to memorize, but just have like treat them as names for the design pressure we see in real systems. So the main focus is the object creation and object boundaries in this part of the video. There'll be a separate video for structural design patterns. So by the end, I hope that you can hear a design problem and pick the right pattern from the pressure it is having. So because this is how we actually design in real world systems, that we start simple and then depending upon what requirements we have, we change the pattern. So you can see like basically we have creational and structural design patterns. So in this part, the focus is the object creation, object boundaries. Creational pattern basically will tell you what when the code is confused and when objects are built, selected or shared, or how you want to build them. Structural helps in how those different objects are wired together. So this is the building part. This is like how they are wired together. And the goal here is basically simple: to hear a requirement, identify the pressure, and choose the pattern that solves it. So, like as I said before, do not learn all the patterns as a flat list. It is a very bad flow if you just read them as factory, builder, strategy, adapter, observer. You will get confused. A better flow is that you first learn about the category, the problem it has, the pattern we have to use, and the trade off. Obviously, there's no one design pattern which is suitable, or like even different design patterns suitable in one example. um, there are obviously trade-offs depending on the specific business use case and the problem you're trying to solve. So I'll also have a best slide frame which says what is the pattern, where does it fit, and when do you should use it. So like basically there are three main buckets, as I said, which is creational, structural, and behavioral. In this video we are going to focus only on creational and structural, otherwise the video is becoming too long. It will become too long. There is another type of design pattern which basically focuses on the type of MVC, MAV, and MVVC, but that is not generally used, and typically I've seen it being discussed mainly in front end operations. So let's start with creational and structural. Under creational, I'll explain about factory, builder, and singleton. In structural, we'll talk about adapter and facade and decorator pattern. So for this, I'm going to take an example of a food delivery system. It is useful because it basically creates the same design we see in real backend systems. You need the order to be built, you need the pricing to be handled, the life cycle, the fraud rules, you need to have notifications, you need to have a checkout, and you need to have payments as well. So there are many different components, and we'll see that how, according to us, this pattern might fit in basically this design pressure. So creational patterns is that when you have like the pressure is that whenever your object construction it starts leaking everywhere, like you have no clarity upon who is owning the creation, selection, assembly, and lifetime of an object, and it's all over the place, then you might want to look at creational patterns. So basically there are three patterns: factory, builder, and singleton, as I said. And for example, this is just a rough idea you might find with the initial name of the pattern: factory, builder, and singleton. For example, before looking at the right side, you just see that, for example, if you have a checkout object and it keeps choosing between three different card, UPI, or wallet options. So generally you would want to keep these three as separate classes and then have one class to build all of these separate classes. Then there's a situation where the order creation has optional fields and validation. So you can't just keep on dealing with the fields again and again. You can instead use a builder pattern to actually build that object. And then there's a singleton pattern, which is basically used in configs the most. So this is the habit which will improve your design decisions, that do not start by naming a pattern, start by naming the pressure it is solving, and then you choose the smallest pattern which removes it. So basically in factory the pressure is that where should payment type selection live as new payment methods are added. So you can do one thing, like for example, if you want to create a new object, you have a payment object on the left, and then you have an equal to, and then you need to give a name for the whatever type of child object you want. So you can write a logic like if the name, if the type is equal to card, go to card payment. If it is UPI, go to UPI. Or if it is wallet, go to wallet payment. But the problem is that this basically defeats the list of principle as well, because you need, if in order to add a new class, you need to modify the existing one again and again, which is not really what we want to do. So the answer would be rather move the creation choice behind one factory. So you will have a separate class which will be your factory class, and you can have your method as create and then the type. So you can just do a payment.pay and like create the payment type of object here via this factory. And next, whenever I need to add, a new kind of a type, I can just if you see here, you have a checkout which needs the payment factory will choose a concrete type, whether you need a card, a UPI, or a wallet. And if you want a separate, like for example, if I have QR, I can just create another QR kind of a support for this factory and not edit the existing code which is there. So what changes is that the caller stops choosing concrete classes, rather it builds it like via factory kind of a thing. So you send in one time your requirement and you get your specific class back. So like it is not exactly about making the object creation fancy, it is about stopping your repeated selection logic from spreading. And when you need to use it is that whenever many concrete implementations exist and selection logic exist in more than one color. So the key phrase over here is basically like repeated selection logic. And when selection logic repeats, so the trade-off is one more object in the design, but the payoff you get is that the new payment types, they change one creation boundary instead of leaking into checkout, test controller, and various other code. So you can see you can just add one extra class whenever you want, instead of having a type equal to QR, and then in every subsequent object, for example checkout, it needs to handle separate type of checkout separately. You again need to have a if type equal to this specific QR and then the handle for that. So use this only when like avoid it when there is just one implementation on already you have a specific set of choices which the caller owns. For example, if I just had QR or card here, obviously I would not go ahead and make a factory for this. And the trade-off is basically one extra object but removes the scattered type checks. And sorry, the basically the practical takeaway is that the checkout now depends on the payment contract basically. So this checkout, it depends on the payment contract. And what happens is that it asks for a payment role, the factory gives you that specific role, what is the type of object you want. And this would keep the object creation in one place, and rest of the system talks through a stable interface. So basically the takeaway from this is that the payment factory, let's check out depend on the payment contract, as I said. But you should not say that you just use factory because object creation exists, because that will be wrong, and that might be over engineering at one point. So let's move on to the next pattern, is a builder pattern. So this is useful when you want to construct an object that has become a workflow. So a object is rarely just two or three specific fields. It has extra fields, obviously, like items, address, coupon, delivery slot, no details. For example, you would have in an order. So once the constructor, if you start making the constructor and it has these arguments, that's argument one, two, three, and then you keep on adding four, five, six, and maybe some of them are optional as well. So it's very easy to create the object incorrectly, to write incorrect code. You might miss one specific argument in there, or you might basically mess up the position of the argument. So with builder, what you see here, right? Like instead of this, you basically do it something like this. So it will make the creation path very explicit, because you are building the object one by one upon the another. So the uh, basically this is one of the strongest design patterns you might use when optional fields are there, or maybe you want to have mutually dependent fields, uh, which might make the constructor unreadable. And if the object is kind of smaller, then you can just use a normal constructor or factory method. That will be enough for you. But if you have a big construction path, obviously go to a builder pattern. And what you can do is basically combine these two. For example, instead of this, if I had something like this UPI over here. So maybe it might also be that this UPI is basically created with a lot of optional fields. So you create the UPI object along with these fields, and then you use builder on the above it to create the payment object. So there might be multiple design patterns as well. In one set of code, you just need to know when to use what. So use it when this object creation is complex enough that the caller site no longer explains what is being created. Um, Avoid it when it has a simple like shape, and it is like adding a builder for every like design choice. It's a very common over engineering problem. So the pattern should give you safety and readability and not just become a fluent API when you can just use it everywhere. So you should not never say that you just use a builder for every model class you find or just keep on appending things to it. Is that you would only use it in the situations where you have to construct the class input step by step and also validate it before each build, and then return a final object which is already safe for the other objects to consume. Moving ahead, we have the singleton pattern. So it is about mostly lifetime control and not convenient access. This distinction actually matters because, for example, if you have in this order system, you have three separate type of configs, right? So uh, basically, these might may genuinely be one shared infrastructure, definitely, and like for example, checkout, payment, and support, you might have just one object for all of the different users. Unlike the situations where you have order, cart, or user session, those are like native to each user. So it cannot be a shared session. So it needs to, these things we can actually put it in a shared context kind of a way or a shared object kind of a way, basically. And there's one danger here, though, which is that you should never add any kind of a business state logic in here, because it will become like it becomes kind of unsafe to add any kind of a business logic over here. Which is by business logic is, I mean, is, for example, if you want to basically select this product or that product, or basically login kind of a thing. So you don't want this. You only want this for basically services mainly. So if you have a checkout service, payment service, or support service, or example, if you have all of those in one app, you can actually keep a single config object, and in that config object you can keep on adding different sub configs, so that you have one single class. And when you are creating this class, what you would generally do is that you would have like, for example, if you have like config, so you would have if you are creating it with environment variable, so you will have hold on, yeah, from environment, and then you have the object. So you would have a situation, if the object already exists in it, then just return it, otherwise create a new object. This is what generally is followed in a singleton pattern. And then when you should use it is that, as I said, whenever one truly shared interface object is there, and avoid it for domain data where the data belongs to a user request, order, cart, or a workflow. The trade-off is that it is convenient, but it creates hidden global coupling. For example, if you move these configs in one place and then you try to create it, so it can actually create very hidden coupling, which you might realize very later in the code and might be difficult. So the restriction you need to follow is that use it only for infrastructure such as configuration or registry access. I'm saying repeating this, I know, but it's very important you understand this, and not for order, cart, or use state. So this distinction basically makes the pattern safe. And yeah, this is the concluding line from it. So just a creational recap on this first type of design pressure you might have. And the three different patterns is that whenever there are many concrete types, go for a factory pattern. Centralize the choice of the pattern of the sub object you're going to make. When there are many construction steps, go for a builder pattern. It makes the object assembly readable. One shared infrastructure object, go for a singleton pattern. It and make sure you share it very carefully. The next kind of design pressure which we feel, like the next category, is that structural category. As you understand, by structure you basically mean how you want to arrange or link the different things together. So the decision lens basically here becomes what boundary or composition problem you are trying to fix in this. And it asks like what boundary is broken. For example, if you have three examples over here, is that payment gateway does not match your app. For example, you have your app, and then the payment gateways, objects, and the API calls, they are very different from what you would have, or maybe there's some legacy code which does not match the current version. So what you might want to use is an adapter version over here. Is that basically you have those APIs, and then you have your APIs, and then you write a adapter class to basically make them fit together, uh, so that they can talk to each other. So this was about adapter. In the second problem you have is that, for example, the checkout coordinates five different kind of services. So the caller is exposed to too much subsystem orchestration. So you might want to use a Facade kind of a service, so that like, instead of the whole orchestration becomes a little bit simpler. We'll discuss more when we come to this. And then you have the third kind of a system, that notification. You might need retry logging metrics in it. So Decorator generally becomes the best fit for it. It's because, like, for example, you have the notification, and then you want to add a specific kind of a feature to notification to make it enable, to make it have logging, or to make it have metrics. Or even when you use Spring Boot, the whole system runs on decorators, to be honest. Or even in Python data classes, you might have seen a lot of decorators. So this is actually really, really common decorator design pattern, um, because it's actually very well embedded in a lot of SDKs you would use. So let's move ahead. So adapter, as I said, is the pattern you reach when an external interface starts shaping your internal code. Payment providers are the classic example. One gateway will say capture, another will say charge the user, another one wants the invoice field. So if these all of these shapes they start leaking everywhere, the app slowly becomes a collection of just vendor specific branches. Then for this reason, what we basically do is that we use the adapter pattern to create a boundary between all of these different operations. So the domain can talk to a payment port like with a language like charge order or refund payment. The adapter would then translate it into, for example, this is Stripe, this is PayPal, or maybe any other vendor specific API. So this is not basically just a design pattern move, it is also a maintainability move. It keeps the domain model stable when vendors change. So example, if you want to add a new vendor, you just create another support in the adapter for it, so that it supports that specific payment provider. And you see, right, if you have a Razorpay, Stripe, and PayPal, you would want to wrap the external shape behind your own interface. Razorpay adapter API gateway.charge order. And this actually internally adapts to all of these specific vendor specific APIs which are there, and calls them. And use it mainly when you have an external legacy or third party interface which do not match your domain. The pressure is mainly interface mismatch when vendor details are spreading throughout the domain code. Avoid it when the interrogation is tiny, because you won't want to over engineer things. So because translation layers, if you write them right, they have a cost of maintainability, and then of writing as well, creation as well. So basically avoid it in those situations. So the practical the trade off is that it would obviously add translation code but protects the domain boundary. So the end APIs are still within the adapter code, it's not with the main user. So if you want to access anything with the end API, you need to actually pass it through the adapter and then access it in the main app or the main system you are running, service you are running. So the design takeaway, as you saw, is that the payment port adapter keeps checkout in the app's domain language, and the supporting adapters, it basically handles the vendor specific calls. So never let vendors fields spread through service. You would rather use like something like an adapter to actually convert them to a language which your app is understanding. The next structural pattern is Facade design pattern. So it is basically used for hiding subsystem complexity from the caller. Checkout over here is actually a good example because it touches various things. So it touches the pricing, inventory, payment charge, order creation, and all that. So if you have a controller, right, you won't do not want to remember all of this. That first you are calling this one, then you are calling this, then you are calling this. Sorry for my bad handwriting. Then you're calling this and then this. You might want to wrap it behind one door, and then this door actually calls one of them one by one. Or maybe if you even want to call them one by one, you call it via this door instead of actually writing the logic for it. So the main thing is to expose one simple entry point over the subsystem. As you see here, from the checkout only, we are calling all of the REST services. So the callers have one entry point for them. And use it when a common workflow that spans over multiple subsystem calls. The pressure here is when you have a caller complexity, not just the existence of many services. If you have many services, they have different ways to call them, or maybe different areas to call them. You do not want to use this. Use it only when your caller complexity is becoming very large, and do not make it a dumping ground for our business logic. Bad Facade is basically just you might have a lot of different broken logic, and then you name it one big class, and you call it, and you say that the design is improved. Do not make that big bad renamed god class. So just expose a small number of stable operation and delegate the real rules to the components. The basically, yeah, as I said again, this is the trade-off, that it must just only be orchestration and not actually become a god class. And the practical takeaway is that this checkout facade exposes one place order operation, and this pricing, inventory, payment, and other services, they stay separate underneath basically. So moving ahead to the decorator design pattern, structural design pattern. It is useful when the core behavior is changing, but the operational feeds around it, right? They keep adding, or you might to add it, or you want to edit this separately in some space. So, for example, if you have a notification service, um, SMS or email might send the message. You have logging around in, you have retry failed, you have a record message. So, what happens is that this all of this, if you keep on writing it, it becomes very complex and hard to actually manage. So too many this too many compositions, separate compositions, it might be very difficult. So generally, if you want to use a decorator pattern, you can actually wrap them one object within the other, to wrap it with different behavior layers. This is one way of doing it. Another way is via the annotation. So you use annotations, like in Spring Boot, you do it in Python data classes, as I said above. You just use some specific annotations, and they actually handle a lot of the logic for you. They can actually make or break a class basically for you. Uh, so use it when optional behavior layers can be composed on one core object, and avoid it when the wrapper order is unclear or the chain becomes impossible to debug. It is a flexible composition, but too many layers, it can actually hide the execution flow. So what I would say is that you have wrapped all of these classes with the decorators, so that the overall behavior is very understandable, and you don't need to call all of this separately. But there is a catch in that, which is that too many wrappers can actually make the execution flow hard to debug, that in which wrapper you actually are getting some specific error. So that is why the decorator chains, it should be explicit, named well, and used for behavior that generally composes around a stable interface. If you want to have a recap, is that whenever external API is not fitting, you use the adapter pattern to translate into your interface. Subsystem is too noisy, use a facade pattern to expose one simple entry point. Optional behavior layers, use a decorator to wrap instead of modifying the class. In the next video, most probably will be looking at at the behavioral design patterns, which will be strategy, state template, method observer, and command chain. Um, so if you like this, please leave a comment and make sure you subscribe. And if you have any suggestions, complaints, or anything you want to share, please drop a comment. I will take a look at it. Thank you.